Hello everyone, myself Dr. Amit Kumar Yadav. I am going to start basic concept related to say neural network. I am assistant professor School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. So first we will see some motivation regarding development of neural networks. So biological inspiration. So these neural networks, it's it is inspired by structures and function of human brain. The basic idea is to mimic the way neurons in the brain work to process information and learn from experience. Pattern recognition. So neural networks excel at pattern recognition tasks such as image and speech recognition. The motivation here is to create a system that can automatically learn and recognize complex pattern in data similar to how humans do. Machine learning achievements. These neural networks, it acts as a fundamental units of machine learning. It include development of neural network architecture, algorithm, and say training technique, which is motivated by desire to enhance capability of machine learning models, which allow them to handle more complex tasks and dataset. Computational power. Advanced computational power, such as powerful GPU, called as a graphic processing unit, and say TPU, tensor processing unit, enables training of deep neural networks. This motivated researchers and engineers to explore more complex and deep architectures. Then say here big data, increasing availability of large data set motivated development of neural networks. These models utilize extensive data set for training, allowing them to learn complex relation and patterns from massive amount of information. Improved algorithm. Innovation in neural networks architectures and training algorithm such as backpropagation, dropout, and batch normalization have played a crucial role in the success of neural networks. So continuous effort are being done for enhancing these algorithms to the ongoing development of more efficient and more powerful networks. Application in various fields. The neural networks have shown success in diverse applications, include computer visions, natural language processing, speech recognition, and gameplay. The versatility of neural networks has motivated their adoption across different domains. Autonomous system neural network development is important for creating say intelligence and an autonomous system. Its applications such as self-driving cars, drones, and robotics. These benefit from neural networks' ability to make decisions using input data and adapt to changing environment. Then what are say research challenges? Neural network poses challenging uh, tasks in terms of optimization, generalization, and say interpretability. And nowadays, researchers are motivated to address these challenges, pushing the boundaries of what neural network can achieve. Industry demand. So, advanced AI technology demand in industry accelerate the development of neural networks. Businesses seek solutions which effectively analyze and make prediction from large data set, leading to widespread adoption of neural network based approaches. Now, first here we will discuss say biological neural networks. Our brain composed of say 10 million neurons, each connected to about say 10,000 other neurons. Here each neurons receive electrochemical inputs from other neurons as a dendrite. If the sum of these electrical input is so much powerful to activate the neuron, it transmits electrochemical signals along axon and passes this signal to the other neuron whose dendrites are attached at any of axon terminal. Then this attached neuron may then fire. Neuron fire only if total signals received at cell body exceed a certain level. So therefore our brain composed of these interconnected electrochemical transmitting neurons. From a very large number of extremely simple processing unit, each performing a weighted sum of its input and then firing a binary signals. If total input exceed a certain level, the brain manages to perform extremely complex tasks. This is the model on which artificial neural networks work, or it is based on. Thus far, artificial neural networks haven't even come close to modeling the complexity of brain, but they have shown to be good at problems which are easy for human but difficult for traditional computer, such as image recognition and prediction, which is based on say past knowledge. Now, perceptron, it is just a mathematical model of biological neurons. While in actual neuron, the dendrites receive electrical signal from axon of other neurons, and in the perceptron these electrical signals are represented as a numerical value. So at the synapses between say dendrites, these part are say synapses between dendrites and axon, electrical signals are modulated in various amount. This is also modeled in the perceptron by multiplying each input value by a value called as beta. And actual neuron fires and outputs signals when total strength of input signal exceeds a certain threshold value. We model this phenomenon in a perceptron by calculating the weighted sum of input to represent the total strength of input signal. As in biological neural networks, this output is fed to other perceptron. So, what are say biological neurons? So, this is the schematic diagram of say biological neurons. Here we are having main components such as say dendrites, soma, synapses, and axon. Now, what are say difference between say artificial neural network versus say biological neural networks? So in biological neural network we are having soma, which is same as node in artificial neural network. In dendrites we are having say biological neural network, which is same as input in artificial neural network. Synapses in biological neural network, it is same as a bait or interconnection in artificial neural networks. Axon in say biological neural network, it is same as a output at say artificial neural networks. So if we see the say mathematical model of say perceptron, here we are having input x1, x2 up to x3 up to xm. These are inputs, and the connecting bit here w1, w2, w3 up to say wm. And here we are having this summation point, and it will go pass through here yn, and it will pass through the activation function. After activation function, we will get here output. So how we can write this equation? Here net input, that will be equal to x1 into w1 plus x2 into w2 plus x3 into w2 up to 3 xm into wm. So how we can write here net input yn summation of I is equal to 1 to m xi into say wi. So how we can calculate the output can be calculated by apply activation function over the net input. So here output is equal to function net input calculated. So what are say various types of activation function? So first one, here we are having say sigmoid function. This is say graph of sigmoid function, and it varies from say 0 to 1. The mathematical expression of sigmoid function is say y is equal to 1 by 1 plus e raised to power of minus x. Next we are having say hyperbolic tangent function. It varies from say minus 1 to 1. The activation function here y is equal to e raised to power x minus of e raised to power minus of x by e raised to power x plus e raised to power of minus of x. Then we are having this rectified linear input. It is called as a ReLU function. The activation function, mathematical expression of rectified linear unit, that is ReLU function, is given as y is equal to max of 0 and x. Then we are having this leaky ReLU function. Leaky ReLU function here, max of say alpha x comma x. Here alpha is a very small constant, say 0.1. Then we are having exponential function. So here y is equal to x, x greater than or equal to 0. and if x is less than 0, alpha e raised to power x minus 1. So how we can represent this input? So here input A1, A2, A2 up to AN. It is connected with say corresponding bit, say W1, W2 up to say Wn. After this, it will pass through this summation layer, this part summation layer. So here all bits say A1 into W1 plus A2 into W2 up to say AN into Wn. It gets a at this point sum up, and it will pass through the activation function. Okay, so these are say different types of activation function. We can use here different types of activation function. After activation function, here at this point we will get the output. So here output is equal to function net input calculated. Now what are say commonly common type of say activation function? First one say step function. Here step function say varies from range from say 0 to 1. Mathematical expression of step function say it is 0 when z is less than 0. It is 1 when z is greater than or equal to 0. So when we see this one, it is 0 when z is less than 0, and if it is greater than 0, here its value is 1. Next here we are having the signum function fz. The range of this signum function is say -1 to +1. Its value is -1 if z is less than 0. Its value is 0 if z is equal to 0. If value is 1 if z is greater than say 0. Next here we are having this linear function fz is equal to x. This is a linear line, and the range of this linear function is a -infinity to +infinity. Then here we are having ReLU function. Fz is equal to 0, z is less than 0. Fz is equal to z, if z is greater than or equal to 0, and it varies from say 0 to infinity. Then here we are having sigmoid function. Fz is equal to e raised to power x by e raised to power of x. This is the graph of the sigmoid function, and the range of this function is from say 0 to 1. The hyperbolic tangent function e raised to power z minus of e raised to power of minus of z by e raised to power z plus e raised to power minus z. This is the graph of say hyperbolic tangent, and it varies from say -1 to say +1. Now, what criteria on which we have to select activation function? If the problem is of say regression type, we have to select linear activation function. If it is say binary classification, then activation function will be sigmoid activation function. And for multi-class classification, activation function is a softmax. For multi-level classification, activation function is a sigmoid. For convolutional neural networks, activation function should be ReLU. For recurrent neural network, the activation function should be tan hyperbolic or say sigmoid activation function. Now, on the basis of this discussion, we will take one say simple numerical to understand this concept well. For networks shown in figure, calculate the net input to the neuron. Here we are having node x1, x2 up to x3. Corresponding to this node, we are having input say 0 0.3, 0 0.5, 0 0.6. And between this node and this neurons y, there is a connecting weight which is given by here say 0 0.2, again here say 0 0.1, again here say minus of 0 0.3. Now x1, x2, x3 we have given in say matrix form, say 1 cross 3. So we have just written here input 0 0.3, 0 0.5, 0 0.6. Then here we are having the connecting bit, say W1, W2, W3, and we have written here say 0 0.2, 0 0.1, say minus of 0 0.3. The net input can be calculated as yn is equal to x1 into say W1 plus x2 into say W2 plus x3 into say W3. Now yn here, here we are having say 0 0.3 into 0 0.2 plus 0 0.5 into 0 0.1 and 0 0.6, here we are having minus of 0. So net input here, by using simple calculation, we are getting here say net input as say minus of 0.07. Second numerical, calculate the net input of the network shown in figure with bias included in the network. Here we include the bias of value 1 and say connecting bit here say 0.5. So here what are say inputs we have to show first in the matrix, say x1, x2 and this connecting bit. So 0 0.2, 0 0.6, 0 0.45. What are say connecting bit W1 say W2, here 0 0.3, here 0 0.7. The net input can be calculated as say net input here we will put here bias plus x1 into say W1 plus x2 into say W2. We put here net input, say bias here say 0 0.5, 0 0.45, here x1 into W1, here we are having say 0 0.2 into say 0 0.3 plus 0 0.6 into say 0 0.7. Here net input say 0 0.45 plus 0 0.06, here we are having say 0 0.42. So when we will add this one, we are getting here say 0 0.93. What are say basic learning rules? So learning rules, it refers to network adjust its parameter or weight based on inputs and say desired output during training process. The different types of learning rules. First one here we will take say Hebbian learning rule. So it is named after psychologist Donald Hebb. This rule states that cells that fire together is wire together. It means if two neurons are activated simultaneously, the connection synaptic bed between them is strengthened. It is used in say unsupervised learning scenario in which network learn to recognize patterns without explicit label. Then here we are having say error correction learning say delta rules. It is a type of say supervised learning approach where network adjust is based based on difference between desired and predicted output. So the common type of error correction rule or delta rule known as say withdraw half rule. So the error is say difference between actual output and say desired output. So based on the error, the bait get updated, and this process is continue iteratively until the error converges to an acceptable level. So these learning rules form foundation of complex and advanced algorithm which are used in say neural network training. Combination and variation of these rules such as backpropagation, stochastic descent and reinforcement learning is developed to address a specific challenge and improve learning efficiency. The learning rule choice depends on type of problem, the nature of data, and architecture of neural networks. Next here, Mcculloch-Pitts neurons. It is known as say threshold logic unit. It is proposed by Warren Mcculloch and Walter Pitt in 1943. It laid the foundation of say development of artificial neural networks. Each inputs is binary. It means that it take either say 0 or 1. Each input is associated with bit which represent the strength of connection between the input and the neuron. The threshold neuron has threshold value. If the weighted sum of the input exceeds this threshold, neuron fires output 1. Otherwise, it remains inactive, output as 0. Mathematically, it can be given by this equation. Y is equal to 1 if summation of say wi into xi is greater than or equal to threshold. Otherwise, it will be 0. So y is the output of the neuron. Means neuron will give the output if summation of say binary input and its corresponding bit is greater than or equal to threshold. Wi represent bit associated with input xi. The summation wixi calculates the weighted sum of the input. The threshold is predefined constant. Biases and threshold in neural networks. In neural networks, bias is an additional parameter added to neurons. It represents tendency of neuron to fire even when all inputs are 0. It is similar to the intercept in linear regression. It fit more complex pattern by shifting activation function curve up or down. Threshold. In contrast to Mcculloch-Pitts neuron models and older neural network, threshold represent a fixed value. that the weighted sum of input must surpass for the neurons to activate. If weighted sum of input exceeds, say, threshold, the neurons output the signals, otherwise it remains inactive. If the sum of input crosses this boundary, the neuron decides to fire. How we can represent this with the help of this figure? Here there is no bias, here input x, here output as a function of say W0 into x. In bias term, here input, here bias, here W0 into W1, here output W0 into x plus W1 into bias. Linear separability. So here it is a concept in say machine learning and pattern recognition, which means where classes or categories can be separated by linear decision boundary. Try to see here, these data are say linearly separable because we can draw one line between these two data. N represent non-sold, S represent sold. It is a statics between say price and area. But here we cannot draw any non-linear separable line at this point. Hebb'srule. It is proposed by Donald Hebb in 1949 to update weight of neural connection between neural networks. It indicates neurons that fire together, wires together. So here, the connection between say two neurons xj and xi, here wij is equal to xi into xj. Hebbian learning rule. First of all, we set all weights to 0. Say wi is equal to 0 for I is equal to 1 to n and bias to 0. For each input vector, yes, input vector, here we are having t say target output vectors. So we repeat step 3 to 5. Then we have to set activation for input unit with input vector say xi is equal to si for I varies from 1 to n. Then we have to set corresponding output value to the output neuron, that is y is equal to t. We have to update weight and bias by applying Hebb'srule for I is equal to 1 to n. So here new weight is equal to wi new is equal to wi old plus xi into y. Bias new is equal to bias old plus y. Perceptron learning rules. Each connection in a neural network has an associated weight which changes in course of learning. Calculate the output value on the basis of a set of record for which we can know the expected output. Here, network compares the calculated output value with the expected value. Next, calculate an error function which can be sum of square of error occurring for each individual in the learning samples. So here we calculate the error function with these symbols. So Eij and Oij are the expected and obtained value of the jth unit for the ith individual. The network then adjusts the weight on on this error difference. Check in each time to see if error function has increased or decreased. In say delta learning rule, which is developed by say Bidrow and Hobb, it depends on say supervised learning. It states that modification in synaptic weight of a node is equal to say multiplication of error and input. So here uh, this is called as a learning rate eta. T is the target, y is the output, xi is the input. Um, so with the help of the difference between error, in error, the weight get adjusted. The weight get adjusted. Now, architecture of say neural networks, it consists of say large number of artificial neural networks. So primary it has say input layers, hidden layers 1, hidden layer 2 and output layers. So in between input layer and hidden layer there is say so many connecting bits. And in neurons we will find say activation function based on say different application. Input layers accept inputs in several different formats which is given by programmer. Hidden layers, it is between input and output layers which perform all calculation to find hidden patterns and features. Then in output layers, input goes through a series of transformation using hidden layer which finally results in output that is conveyed using this layer. Artificial neural networks takes input and computed the weighted sum of inputs and include a bias. How do artificial neural network works? It can be represented as weighted directed graph where artificial neurons form the nodes. The association between neuron output and neuron input can be viewed as a directed edge with weight. These neural networks receive input signals from the external source in form of pattern and image in form of vectors. So here x1, x2 up to xn, input layers and hidden layer, there is so many connecting bits. So on output layer, the error is calculated and based on this error, the connecting bit are adjusted so that error can get minimized. So what are say different applications of say artificial neural networks? We are using say in text classification, named entity recognition, part of speech tagging, machine translation, means converting one language to another language, semantic parsing and question answering. Then we are having paraphrase detection, speech recognition, multi document summarization, character recognition, then spelling checking. Advantage, here we are using say fault tolerance. If one or more cell of ANN get corrupted, the generation of output will not get affected. Parallel processing to perform multiple function simultaneously. Training, learn from events and make decision based on similar event. Gradual corruption, artificial neural network does degrade and slow down over time. However, ANN does not corroded instantly. Speed, ANN are put to use in case where quick evaluation of learned target function is necessary. What are the disadvantages? Lack of transparency, the functioning of NN is not clear, and solution reached do not come with explanation as to how and why they were reached. Difficulties in introducing problem to artificial neural networks. So it works with numerical information. Therefore, before you introduce your problem to artificial neural network, we have to convert it into, say, numeric value. No rules for structure. Artificial neural network have no rule that govern their structure. You can reach an appropriate network structure through trial and error and experience. Here we are having say single layer net for say pattern classification. So the basic layers here we are having say input layers, then we are having this connecting bits, then here we are having activation function, then here we are having output, and from output layers it consists of say single neurons which is used for say binary classification or multiple neurons for multiple class classification. The output of this neuron represent the predicted class level. Now we will see some numerical implement add function using Mcculloch-Pitts neurons. Take binary data. So we will see here truth table for and this one. So in Mcculloch neurons, only analysis is performed. Therefore, we take a connecting bit say W1 W2 is equal to 1. So the network architecture here W1 is equal to 1, W2 is equal to 1. So we used to give here say first 1 1, then we have to calculate this one here we will get 2. Then we will get 1 0. We will calculate say net input. Similarly 0 1 net input, 0 0 1 net input. For AND function output is high if both input are high. For this function net input is calculated as 2. Hence, based on this input, the threshold is set. So the threshold value is set to 2, theta is equal to 2. This can be obtained by theta is greater than or equal to nw minus p. Here n is equal to 2, w is equal to 1. This is called as excitatory, and p is equal to 0. This is called as inhibitory. So here theta is greater than 2 into 1 minus 0. Theta is greater than or equal to 2. The output of neuron y can be written as, say y is equal to f as a function of yn. Now we will see some numerical example on Mcculloch-Pitts neurons. First problem here, a Mcculloch-Pitts neurons has 3 binary input which is given as say x1 is equal to 1, x2 is equal to 0, x3 is equal to 1. The neurons utilize equal weight of 1. Now we know that these weights say varies from say minus 1 to plus 1, but here we assign weight of value 1 for all inputs. Inputs here given x1, x2 and x3. And the threshold value say theta is equal to 2. Now we have to determine the output of the neurons. Now first of all, how we have to proceed for this type of solution? So inputs which is given as say x1 is equal to x1, x2 and xt. First of all, we have to write all these inputs in a matrix which is denoted by say small x, and this value of input is given and we have to put in this way 1 0, 1, it is given. Now bait value is given as 1, so we have to put this as 1, 1, 1. And threshold value theta here is equal to 2. Now we have to take say baited sum. It is called as say net inputs. How we have to find out say net inputs? We have to multiply the input x1 with its corresponding bit say w1, input x2 with corresponding bit w2, then x3 corresponding bit say w3. Here all bits are equal to 1. Now calculate this net input, that is equal to say w1 into x1 plus w2 into x2 plus w3 into x3. Multiply here 1 with 1 here, plus 1 into 0 plus 1 into 1. When we will compute this part, we will get here 2. Now activation function. This Mcculloch-Pitts model uses a say step function. Here y is equal to 1 if this net input, this one, is greater than or equal to theta, and y is equal to 0 if net input, this one, is less than theta. Since net input here 2, net input we have calculated here 2 as per the problem, and theta is equal to 2. With this part, if net input is greater than or equal to 2, we will get here 1. So here the value is 1. The value is equal to y is equal to 1. Now we will see the implementation of OR gate using Mcculloch-Pitts neurons. First of all, for this, we will draw the truth table of two inputs, say x1 and x2 with OR. So if we take two value x1 as 0, x2 as 0, output is equal to 0. If we take again here 0, 1, output is 1. If we take here 1, 0, then output is equal to 1. Then again here 1, and if we take again x2 as 1, output is equal to 1. Now here, what are bait which we have assigned here? Let us take say w1 is equal to 1, w2 is equal to 1, and we take here say threshold value theta is equal to 1. How activation function works at this point? Y is equal to 1 if x1 plus x2 is greater than or equal to 1, and y is equal to 0 otherwise. So by keeping this concept in mind, first of all, we have to calculate say net input by multiplying the corresponding input with its corresponding bit. Now check here, if we take input x1 is equal to 1, x2 is equal to 0, means this part x1 is equal to 1, x2 is equal to 0, So 1 plus 0 is equal to 1, and here it is greater than or equal to theta, so y is equal to 1. Next we will take x1 is equal to 0, x2 is equal to 0. We will calculate net input, say 0 plus 0 is equal to say 0, and it is less than theta, so y is equal to 0. Next we will take here say 0 0, say x1 into say w1, both are 0, so it will become say 0. It is not greater than 1, so this will follows. So here you are having output 0. Here if we take input x1 is equal to 0, x2 is equal to 1, so 0 plus 1 is greater than or equal to 1 here, so we will get here output as 1. If we get here input x1 as 1, x2 as 0, 1 plus 0 means 1 here is greater than or equal to 1, so here we will get 1. Now if we take input x1 as 1, again if we take input x2 as 1, so 1 plus 1 2, it is greater than or equal to 1, so here we will get value 1. So by this example we can see that how we can use or implement this OR gate with Mcculloch-Pitts neurons. So this what we conclude from here, it works exactly like an OR gate. Now NOT gate using Mcculloch-Pitts neurons. What is the truth table of NOT gate? If input x is equal to 0, output is equal to 1. Now if again if input is equal to 1, output is equal to 0. So here we take here bait, say input here x, we take here bait say -1 w, and threshold value we are taking here say theta is equal to say minus of 0.5. How activation function works? Y is equal to 1 if w into x is greater than or equal to theta, 0 otherwise. So here we are having bait say -1, okay, -1. So -1 into 0, it is 0. It is greater than or equal to this threshold value minus 0.5, so we will get here 1. Here try to see 1 1, x1 is equal to 1, bait is equal to minus of 1, so minus of 1 is greater than or equal to minus of 0.5, no, so it will be 0. So this condition will be followed. So same part we have discussed here. So we have seen here this Mcculloch-Pitts neurons, it works like an NOT gate. Now we will see what are different types of activation function which we can use in say neural networks. So first we will see the sigmoid activation function. Try to see the formula of this sigmoid activation function. Here sigma x is equal to 1 by 1 plus e raised to power of minus of x. If in a problem we suppose this x represents a net input as the hidden layer or input or output layer contain this sigmoid activation function. So with the help of this equation, we can find out the output of a neurons, right? If we put here x is equal to say minus up to here, so the equation will become 1 by 1 plus e raised to power minus of 2. We will do just simple calculation and we will get here say 0.119. If we take x is equal to say 0 here, so 1 by 1 plus e raised to power 0, that will be equal to 1. So this sigma x is equal to 1 by f 2. So here what we will get equal to say 0.5. If we take x is equal to say 2, put here x is equal to 2, that will be equal to 1 by 1 plus e raised to power of say minus of 2. So when we will put all these in this equation, we are getting here say sigma 2 as 0.881. Another activation function, say tan hyperbolic activation function. The equation of this tan hyperbolic activation function is e raised to power x minus of e raised to power of minus of x by e raised to power of x plus e raised to power of minus of x. If we take x is equal to say minus of 1, then we will put here and we will do a simple calculation. What we are getting here, minus of say 0.761. If we put here x is equal to 0, so here we will get here 0. If we put here x is equal to 1, and we will get here say 0.761. So this is called as a tan hyperbolic activation function. What this activation function is doing here, so what will be the say value of say plus 1 0 1? It will bring down its range from say minus 1 say plus 1. Then we are having this rectified linear unit activation function. It is called as ReLU activation function. The equation here we are having say fx is equal to max of say 0x. If we take x is equal to minus of 5, so what is maximum value say 0 and minus of 5, here we will get here 0. If we take here x is equal to 0, max of 0 0, here we will get 0. If we take x is equal to say 3.5, max of 0 and 3.5, here we will get here say 3.5. Then here another activation function. This is called as a leaky ReLU activation function. The equation is say fx is equal to x if x is greater than 0, else alpha x. Here alpha, the value which is given as say 0.01, it is called as a constant. In example, if we take x is equal to say minus of 4, so what we will get here, say alpha into x, because this x value is not greater than 0, right? So therefore we will use this part and we will get here say a minus of 0.0. If we take x is equal to 0, right? So we are getting here x is equal to say 0. If we take here x is equal to say 2, x is equal to say here 2. So here we are getting here say x is equal to 2 fx2. So what we are getting here, say here fx is equal to x is equal to 2, therefore fx is equal to 2. After this we are having this soft max activation function sigma as a function of zi e raised to power zi by summation of e raised to power of zi. What are inputs? Suppose we are taking here input 1, 2, 3. So first we will take here 1 by summation of all these values. Okay, then we will take here 2, then summation of all these values, then similarly for 3.0. So here we are having simple calculation. We are getting here output as this way. Then we will try to see how we can utilize the concept of Mcculloch-Pitts neurons in one simple ANN problem. So here, design a simple artificial neural network problem with two inputs neuron, say x1 0.5, x2 say 0.8, one hidden layer with two neurons, and in these two neurons we are having this sigmoid activation function. Here we are getting say -1 output neurons using sigmoid activation. Then here we are having -1 beta and biases are predefined. Now the network parameters, which is given as say connecting bait between input to hidden, say W11 is equal to 0.1, W12 is equal to say 0.3. Similarly, W21 means second input to first means second neuron of input layer to first neuron of hidden layer is equal to 0.4. The second neuron of input layer to second neuron of hidden layer is equal to 0.2. Hidden to output, say V1 is equal to 0.5, again V2 is equal to 0.6. Biases here hidden, B1 is equal to 0.1, B2 is equal to 0.2. Output here B3 is equal to 0.3. Now hidden layer computation. Net input to hidden layers, hidden neurons H1, say Z1 X1 into W11 plus X2 into W21 plus bias B1. So when we add all these points here, we will get here say 0.53, and it will pass through say sigmoid activation function. So here we are having H1 is equal to sigmoid of Z1. So we will put here all this value and we are getting here output of say hidden neurons H1 at say 0.63. Next, net input to hidden neurons H2. Here we are computing say Z2, X1 into say W12 plus X2 into W22. Here bias value B2 is given. So when we will put all this value, say here 0.5 into 0.3 plus 0.8 into 0.2 plus here 0.2, that is a bias value. So when we will do all this computation, here we are having say 0.49, and it will pass through say sigmoid of Z2. So 1 by 1 plus e raised to power of this value here. When we compute all this part, we are getting here say 0.62. Next here, output layer computation. Net input to output neurons J3 H1 into say V1 plus H2 into V2 plus here bias value. We will put here the output of hidden layer neurons 1. Here V1 is the connecting bit plus here this is the hidden output of hidden layers neurons 2. This is the output plus here bias value. When we put here, we are getting here say 0.973. Y is equal to say sigmoid of say Z3. So once we will put all this value, here we are getting say 0.726. Now given the input